Hi everyone, it's Mr. H here. This video we're going to look at how to simplify using the exponent rules, including the product rule, the quotient rule, and the power of a power rule, amongst other rules. We're going to look at an exponential function application about population, and then we're going to look at all the properties of and sketch the function shown there. So this is designed to be a complete overview of the exponential functions unit in grade 11 functions. But if you're in grade 10, grade 12, or beyond, you'll still find this helpful to gain an understanding for exponential functions. This question says simplify using exponent rules. Now the first question you might have is, what are the exponent rules? Well, I'm so glad you asked. The first one is the product rule. If they have the same base and they're multiplied, we can add the exponents. If they have the same base and they're divided, we can subtract them. That's the quotient rule. The power of a power rule says that we take the power outside and multiply it by the power inside the brackets. The power of zero rule, anything the power of zero is 1. Negative exponent is the reciprocal. And the rational exponent law is we take the nth root of something if it's in the bottom of a fraction that the exponent's raised to. So here's the strategy we're going to look at. We want to look inside to outside the brackets. That's the first thing for these questions. And the second thing is we're going to use the negative exponent law at the very end and only at the very end. Otherwise, you're going to be flipping things a lot and it's going to make your life a lot more difficult. So only at the very end are we going to use that. So let's go and dig into this first one and apply this. So the first thing we're going to do here is working inside to outside. We're working on these inside brackets. So 7 to the power of 2 divided by 7 to the power of negative 1. Well, we're going to use the quotient rule. 2 minus negative 1 means we add 1. And so we can simplify inside those brackets to be 7 to the power of 3. Now that's all to the power of negative 2. So now we can use the power of a power rule. 7 to the power of 3 times negative 2 gives me 7 to the power of negative 6. Now the quotient rule we're going to use again. Because we're dividing, we're going to subtract those exponents, and we can only do that because they have the same base. So 7 to the power of negative 3 minus negative 6 means you add 6, gives you power of 3, and 7 to the power of 3 is 343. Now, 7 to the power of 3 is the final answer because it didn't tell us to get a final answer, it just said simplify. The second question, we're going to use the same idea, but we're going to have a little bit more with the rules applying here. The first one is the power of a power rule. 12 times 0.25 is 3, so x to the power of 3. And then everything else in the numerator is going to stay the same. Now, notice that the power of a power rule has the 6 applied to the 3. That's what my students miss the most. And the x. So 3 to the power of 6, x to the power of 6, and then x to the power of 9 at the end. And that's all to the power of negative 1/3. So now what we're going to do is we're going to apply the product rule by combining the powers of x in the numerator and in the denominator. So 3 plus 9 gives me 12 in the numerator, and then we have 6 plus 9 gives me to the power of 15 in the denominator. Still all to the power of negative 1/3. And you'll notice as well I've not expanded out the 3 to the power of 6 because I'm going to look at that negative 1/3 and that'll likely simplify something for me. So I'm now going to apply the quotient rule, so 12 minus 15, so that gives me x to the power of negative 3. And the last thing now I want to do now is bring that negative 1/3 in. And again, I'm keeping that 3 to the power of 6. I'm not expanding that and simplifying it with the 216. You could do that, but I'm going to do that the way I'm doing it just to make the numbers a little smaller that I deal with. And that I like that, keeps it a little easier. So we go ahead and we multiply the negative 1/3 times 1 for the 216 times negative 3 for the x to the power of 1. And then we get negative 6 over 3 for the power of 3. Now that means I'm going to apply the negative exponent rule to the two numbers. I'm going to bring the one that's in the denominator to the numerator and the one that's in the numerator to the denominator, and then apply these. So 3 to the power of 6 over 3 is 3 squared, and 216 to the power of 1/3 is the third root of 216. 3 squared is 9, and the third root of 216 is 6. So I can simplify that to be 3x over 2 by dividing the numerator and denominator by 3. And so we've applied all the rules but the power of 0 rule. That's how it works. This question says the population of tigers in Africa has an exponential rate of decay of 5% every year. Notice it's a rate of decay. We'll come back to that in a moment. If the tiger population in Africa was 25,000 in 2019, how many tigers will there be in Africa in 2040? And then in what year will the tiger population become half of what it started at in 2019? So the first thing to keep in mind here is the general equation for exponential growth or decay. It's the population after some time is equal to a times b to the power of t. Now a is the starting population or the starting value. That's pretty straightforward here. It's going to be 25,000, which we'll sub in here in a moment. B is a little more tricky, and what we have to do with this is we have to recognize that this is the exponential growth or decay factor. It's essentially what I'm multiplying by each year to get the number I have the next year. So for an exponential growth, what I'm going to do is it's going to be 1, B is equal to 1, plus the growth rate. Now that growth rate has to be listed as a decimal. If it's not as a decimal, then it's not going to be correct. So for example, if you had a 5% growth rate, you list it as 0.05. If it's decay, we're going to write it as B equals 1 minus the decay rate. Now in this case, the decay rate is what we have because it's becoming less every year. And so we write that also as a decimal. So in this case, what we're going to get is 1 minus 0.05, which is going to give us 0.95 in our specific case. So the population after some time is equal to 25,000. That's our starting value, 25,000. And then we're going to substitute in 0.95 for B, as I already mentioned, because of that decay rate of 5%. 1 minus 0.05. So we subtract that, and we get 95%. That's what that means. It's really, I'm going to have 95% each year of the population I had the previous year. So 0.95 to the power of t. Where t, and we have to be specific here, it's the number of years. Sometimes with bacteria or things, you might have number of minutes or hours. But here's the number of years, and specifically since 2019, because that's where we're starting this equation off at. So we have to be very specific with how we define our t value. And so our P is our population of tigers after T years since 2019. So the first question is, how many tigers will there be in Africa in 2040? So now that we set up our equation, we can actually solve that. We take the 2040, we subtract the starting year, we get 21 years, and all we have to do is substitute that into the equation. Really, really simple substitution. You can type that in your calculator. You go 0.95 to the power of 21. Be careful that you don't multiply the 0.95 times 25,000 first. Because if you did and you got an answer for that and then put it to the power of 21, it would be a lot bigger number. So just the 0.95 to the power of 21 and multiply that by 25,000. We get 8,514 tigers. We round that number and we can't have part of a tiger. So there's going to be 8,514 tigers in Africa in 2040, according to this model. This isn't actually true, but this is a model that someone might have. So now it says, in what year will the tiger population become half of what it started at in 2019? Well, half of what it started at is 25,000 divided by 2, which is 12,500. And so we're going to go back to our equation that we had. Population after some time is 25,000 times 0.95 to the power of t. In this case, we don't know what t is, but we do know what that p of t is, that population value is. It's 12,500. So I'm replacing the p of t with 12,500. And I'm going to try to rearrange the equation to solve for t. Now the first thing we have to do if we're trying to rearrange this equation is we have to multiply or divide first. We want to deal with the exponent last. So we're going to divide here to cancel out the 25,000 from the right side. And I get 0.5 or 1/2 on the left side. And so 0.5 is equal to 0.95 to the power of t. And here's where we can use logs. Logarithms are really helpful because when we take the logarithm of something, what it does is it takes the exponent on the one number and it brings it out in front of the log. And so what we're going to do is we're going to write this as log 0.5 equals, we can write this as t times log of 0.95. Now we can divide by everything except the t on the right side, and I get that canceling out the log of 0.95. Now on the left side, I get log of 0.5 over log of 0.95. Don't cancel out the logs. They have to operate on the number that follows. And if I do that properly, I get 13.51 years. Now, remember it's asking for what year the tiger population will become half of what it started in. I'm going to assume that the 2019 population is right at the beginning of the year. So 13.51 years later, after 2019, is 2032 and then 0.51 of that year. So that would be the year 2032. This question asks, for the function f of x equals -3 times 2 to the power of 2x plus 4 plus 1, determine the following showing all steps. Now the first thing is the parent function. Well, that's pretty easy to identify because you just identify what the b value is, what that base is. In this case, it's 2, so the parent function is f of x equals 2 to the power of x. For the y-intercept, we let the x value be 0. We just substitute 0 in and we solve the equation when that's the case. So Negative 3 times 2 to the power of 2 times 0 plus 4, all plus 1. Now, a lot of people assume it's just going to give an answer of 1, but follow the math. Make sure you're actually getting this, because even though it's 2 times 0, you still have the 4 as the exponent on the 2. So that gives you negative 48 plus 1, which is nowhere near 1, as you can see. This is negative 47, not 1. So be careful assuming that it's just going to be 1. Yes, the asymptote is going to be at 1, as we'll do now, but it doesn't mean that the y-intercept will be. So y equals 2 to the x. That's our base function, or our parent function. And we would just say that has an asymptote at y equals 0. It literally goes down to 0 for that. But if it has an asymptote now up at 1, it's been shifted up 1, then that means that's our new asymptote. That's all we have to look at, just that c value that shifts it up or down at the end. And so y equals 1 is the asymptote. Part D says what the domain and range are. And so for any type of exponential function, the domain is always all the possible x values. So x is a set of all real numbers. The range, though, is something we have to think a little bit about. So if it was y equals 2 to the power of x, then our range would be y is greater than 0. If it was negative, as we can see the a value, the leading value is negative, that's going to flip it over the x-axis and make it go down. So it would be below 0. But because the asymptote has been shifted up to 1, it's going to be below 1. And so there we say y is a set of all real numbers such that y is less than 1. Doesn't touch 1, it's less than 1. Now part E says sketch the graph. And there's a couple of ways we can go about doing that. The first thing I want to discuss is just how do you do that with transformations. So remember that the general form of an exponential function is f of x equals a times b to the power of k bracket x minus d. We common factor out the k value so we clearly see where the d value is properly, plus c. And so I'm just going to rewrite that equation I had at the top with that k value factored out so that we can see that the d value is not 4 or negative 4. It's actually negative 2 here, as we'll discuss in a moment. The a value is negative 3, which is a vertical stretch factor of 3. And it also being negative is going to flip it or reflect it over the x-axis. And so we could take any points from the equation y equals 2 to the power of x, and we can apply these transformations through this. So if k value is 2, that's a horizontal compression. And the reason it's a compression is because the factor for the k value is always 1 over the k value. So it's 1 over 2. The d value is going to be negative 2 here because it's x plus 2 means if the general form is x minus d, it's x minus negative 2. That makes it plus, which means it's going to shift it 2 units left. And then the c value is 1, which means it shifts 1 unit up, as we've already discussed with the asymptote. So what you could do is you could take a couple of points. For example, we could take the point 0, 1. That's the point, always the case for any exponential function that hasn't been transformed. And 2, 4. Those are 2 points that are on that original graph of y equals 2 to the power of x. You could then take the y values and multiply them by negative 3, because that's what the a value is doing. Then you could take the x values and multiply them by a half. That's what the k value is doing. And then the d value is also operating on the x value, so you subtract 2 from that x value. And the c value would be adding 1 to the y value you had from before. So in general, what we're doing is we're taking the coordinates x comma y, and to the x coordinate, we're applying 1 over k to it, and then we're going to add d, whatever d is. And to the y coordinate, we're multiplying it by a, and then we're adding c to that. And that's going to give us the final coordinates, and we could translate all those coordinates like that. But I would ask the question, what are the most meaningful points on this graph? What are the things we care the most about? Because it might not be those points that we transform. They might not be much of interest to us. The ones I would argue are the most important are starting with the y-intercept. That's by far the most important. We know that's y equals negative 47, which if you translate 0, 1, and 2, 4, you're not going to get that by translating that. The other key thing we want to look at is the asymptote y being 1. And so because of that, I'm going to go up and down by a scale of 10. And I'm going to go with an x scale by 1. And I'm going to label my asymptote at y equals 1. And so I know that it's coming from below. It's going to go through negative 47. It's going to look something like that. So what I want to do just to get a better sense of the shape is I want to substitute in a couple of x values that are just to the left of that y-intercept. So I'm going to substitute in -1, and when I substitute that in, I get 2 to the power of -1 plus 4 as the exponent, and so I get 2 as the exponent, which gives me -11. And then if I sub in -2, I end up getting, after subbing in, -2. So what I can do is I can label those points on my graph, and you can actually see that that's a lot steeper than I would have originally labeled those curves with. So it's going to go up through those key points. It's going to be a very steep graph like shown. And we can label that with the function f of x equals -3 times 2 to the power of 2x plus 4, all plus 1. Thanks so much for watching. I hope this was helpful. If you want more on the exponent laws and how to apply them with lots more examples, check out the video on the left. The video on the right is all about those transformations, and it looks at them with a number of other different functions and how to apply those transformations A, K, D, and C. So if you want to see that, check out that video on the right. Thanks so much for watching.